All right, we are off to chapter 17. I believe we finished 16, I hope, because I opened this one. So we're going to go with this one. So remember, exam 1 week from today. Yes, 7 and 16 thermodynamics. Yes. Fun thermodynamic exam. Also homework due. Yes, don't forget about that. And 17 here will be exam 4 material. You know, right there before the final. So you take exam 4, give me the final, give me exam 4, I give you a final. Just got to do that all one day. That's a good day. I'm kidding, by the way. Please don't send me your emails or anything. All right, just all right, we'll do it like at least a day before, maybe. Hopefully. All right, chapter 17 is electrochemistry. As the title says, that is redox reactions. So we're going to go over sort of the basics of redox reactions, balancing redox reactions. I'll spit that out. Oxidation numbers, oxidation states, just to make sure everybody's on the same page. Because depending on who you maybe had for first semester, maybe you did more, maybe you did less, maybe you didn't do any of it. Who knows? So at least we will all be on the same page here. Hopefully, when we're done. And then we'll get into really the heart of the chapter, which is galvanic cells and that type of stuff. So we're going to start with redox here. So an electrochemical process are oxidation and reduction reactions, and we use basically the transfer of electrons. So just in case we're not sure about this here, redox reactions are basically a transfer of electrons is pretty much what's happening there. That is, as you may know, one of the 3 reasons why really a reaction takes place is a transfer of electrons. You made water or you made a solid. Basically, those are the big 3 of why something actually takes place, a reaction. Redox reactions are also more specifically classified as things like synthesis reactions, decomposition reactions, single replacement reactions, combustion reactions. They all fall really under the umbrella of redox reactions. And ultimately what's happening in all those cases are electrons being transferred. The good news is redox stands for oxidation. I'm not sure that's a good news. And reduction here. And they always do occur together. So if there's somebody being oxidized, there should be somebody being reduced. And there are actually several definitions of oxidation and reduction. But here in general chemistry, we usually go with the electron definition, which means oxidation, you're going to lose some electrons, and reduction, you're going to gain some electrons. Some people like to remember that as Leo the lion goes grr, or some people like the oil rig is very popular these days. Again, you could put Leo the lion on the oil rig and he goes grr, and you don't have to choose. You can just use them all together in a nice big old sentence there, and everything should be good. So how do we know if like something is being oxidized or something being reduced? There's really sort of a very simple way you could kind of figure it out, and we'll talk about as we go through this. I like to use just a basic number line approach. And I think to the right of 0 are positive numbers, to the left of 0 are negative numbers. And obviously, when somebody gets oxidized and they lose electrons, they actually become more positive, right? Because now they have more protons than electrons. So if you look, as we'll talk about, at the oxidation number of something on the left-hand side of the arrow versus the right-hand side of the arrow, and it's moving in this direction towards the positive side, then you are going through oxidation. Now, obviously, if somebody gains electrons, they're going to become more negative because they obviously now have more electrons than protons. So if you follow the oxidation number from the left-hand side of the arrow to the right-hand side of the arrow, and you find yourself moving this way in the negative direction on the number line, that substance is going through reduction. So that's a really simple way to figure out, what is going on in terms of oxidation or reduction. Just to, again, demonstrate how that sort of works there. If we took something like sodium and reacted with something like chlorine, make a little sodium chloride in this case, maybe balance it like I'm in chemistry class. There we go. And in this case here, if we look at it on the left-hand side, as you may know or don't know or will know shortly, anything that is in its natural state that is uncombined has an oxidation state of 0. So they don't have charges or anything like that. So that would have a zero oxidation state. So would the chlorine in this case. And that is again how it naturally comes. Remember, things really don't get charges until metals and nonmetals kind of come together and be happy with each other. On the right-hand side here, that sodium does have a charge of +1, and the chlorine has a charge of -1 in this case. So if we were just trying to figure out what's going on, we can very simply look at the sodium, and the sodium started at 0 on the left-hand side. And would you look there, it ended up at 1 on the right-hand side, which means it is moving in the positive direction. And sodium here is going through oxidation. The good news on that is if you can figure that out correctly, by default, the chlorine has to be going through reduction, but we could also do the exact same thing for the chlorine. So this was our sodium. If we look at the chlorine here, it also is starting at 0, but on the right-hand side, the chlorine's ending at -1, and it is definitely moving in the negative direction here. So again, that means it is going through reduction. By the way, that is something we should always expect to happen because sodium is a metal, right? And chlorine's a non-metal. And that is always what happens when those two guys get together. The metal's always the one that's going to lose the electrons. The non-metal, right, is always the one's going to gain them. That's how we get our cation and anion, right? They come together to make our ionic bond. This also works really well, for example, if you got a metal on both sides and you want to kind of figure out what's going on. So if I have iron with a +3 on the left and iron with a +2 on the right, is this guy being oxidized or reduced? It is being reduced in this case, perhaps. We are starting in a +3 over here, right? And we're ending in a +2, which means it is moving in a negative direction. And this guy is going through reduction. So that's just a really simple sort of way that you could figure out oxidation or reduction. Any questions on that there? So as I mentioned, in this process, we do have really electrons being transferred. So once again, if we look at this example, we have magnesium by itself has a 0 oxidation state. Oxygen is how it naturally comes, also has a 0 oxidation state. When those two guys get together, that's when our magnesium is going to get a +2 charge and our oxygen is going to get really a -2 oxidation state. And once again, we could, if you're not sure, just kind of look on the number line here. So once again here, magnesium is starting at 0, ending at +2. So it definitely is going through oxidation. The oxygen is starting at 0 and ending at -2, becoming more negative. It is going through reduction. We can write what are referred to as half reactions. And one half reaction is the oxidation half reaction, and one half reaction is the reduction half reaction. They are called half reactions because they're half of what is going on, and if you add them together, you get the whole reaction, right? Two halves make a whole. This is the oxidation half reaction, and we know that because in an oxidation half reaction, the electrons are on the product side, and that is like those electrons are being given off. And in this case, we have our reduction half reaction, which is over here. And we know that's the reduction half reaction because the electrons are a reactant in that case, like they're being gained. By the way, we have 4 electrons here because we wanted 2 things balanced, and each magnesium is going to lose 2 electrons. And since there's 2 magnesiums, that's a grand total of 4 electrons. By the way, the total number of electrons should always be equal to the amount of electrons that are lost. So if somebody loses, for example, a total of 4 electrons, somebody else will be there to gain 4 electrons. Once again, as I mentioned, we could add these half reactions back together. And if you have a basic sort of half reactions here, what you want to do is add them back together. But before you do that, you should always make sure that the number of electrons in each half reaction are always the same number. And they may not always be the same number. In this case, they are. But before you add them back together, you do want to make sure that they are. So for example, let's just say we had this as our half reaction here. And, we had the other guy just like it was. before we would want to add these together, we would need to truly multiply the top half reaction by 2, and that's going to give us the same number of electrons in each of them. In some cases, you may have to multiply one half reaction by a number. In some cases, you may actually have to multiply both half reactions by a number, but the goal is to get it to the same number of electrons. Again, the idea there is however many electrons somebody loses should be how many electrons somebody gains along the way. And obviously, if we add these together, the one thing that should always cancel out completely are the electrons. So they should always cancel out completely, which also means that if you're writing half reactions, you should never have electrons on the same side of the arrow because they will never cancel out. So you screwed something up for sure. Yeah, I don't want these one thing out. It was messed up. Maybe both if you put them on the wrong sides, both. But they never should be. Everybody on the left-hand side stays there. Everybody on the right-hand side stays there. That's an ionic compound, so they'll actually come together there and make our ionic compound, and we'll get the overall reaction that is taking place here. Now, why is electrochemistry so important? Well, we can actually use these electrons, as we'll talk about, to do some type of work. It's kind of the idea of batteries, right? Electrons go out or along a wire, powers your device and goes back to the other side. And so we can use this sort of electron transfers to power something and do some type of work. I feel like there's going to be a delta G somewhere in this next chapter here. It's a little preview. I know it will come soon. All right. Now, in addition to things being oxidized and reduced, we also have what is referred to as the oxidizing agent and the reducing agent. And that is actually something different than if you were asked what is being oxidized and what is being reduced. So those are actually two different questions. So to confuse things even more, the oxidizing agent is always the substance that gets reduced. So whatever substance is actually getting reduced is what is referred to as the oxidizing agent. And the reducing agent is whatever substance is getting oxidized. So why are they called that? They're called that because the oxidizing agent gets reduced, which means it is gaining electrons. So the only way it could gain electrons is it has to cause the oxidation in the other thing to lose those electrons. That's why it's referred to as oxidizing agent. The reducing agent, a similar explanation. That is the substance that gets oxidized. So because it's going to lose those electrons, it is going to cause somebody else to accept those electrons and get reduced. So the easy way to remember it is if you're sort of asked about the agent, it's opposite of the name. So if you're asked about the oxidizing agent, it's the thing getting reduced. And if you're asked about the reducing agent, it's the thing getting oxidized. So in our example here, as we just went through, this was our guy that was getting oxidized. This was our guy getting reduced. That means that the magnesium here is actually our reducing agent, and the oxygen here is our oxidizing agent. So again, that is how that works. By the way, that is also the side of the arrow that you find all those things on. So if you're asked what is being oxidized, what is being reduced, what's the oxidizing agent or the reducing agent, you find all those guys on the reactant side of the arrow. Yeah, so that's where you find all those things. So ultimately what is happening in this case is magnesium is sending some electrons over to oxygen because it is causing those electrons to go to the oxygen, is causing oxygen to be reduced, hence magnesium is the reducing agent. Oxygen is going to cause magnesium to lose those electrons, causing the oxidation of magnesium. Any questions on that there? So let's take a look at another example here. Once again, we have calcium in a standard state, no charge, no oxidation state on either of those. When they come together, we have our +2, our -2. Once again, we do have a metal and a non-metal, so we should know, but just in case, calcium starting at 0, ending at +2. So again, becoming more positive. as we should expect. This is the guy going through oxidation. Oxygen starting at 0, ending at -2, becoming more negative. And this is the guy that is getting reduced in this case. Once again, you can see we have our two half reactions here. Oxidation half reaction, reduction half reaction. Add them together gives us our overall reaction back in this particular case. My 2 got lost there. I'll put it back up there just in case we need it and that kind of thing. All right, so as I mentioned before, oxidizing agents always gets reduced. Reducing agents are always the things get oxidized. Um, so if we look at this here, why don't you take a moment and decide what is the oxidizing agent, what is the reducing agent? All right, so let's take a look. That is, I think they call that tin 4 oxide. So I'm going to say the tin here has a +4 oxidation state. That's oxygen, which typically always has a -2 in most cases. That is carbon by itself, which is probably a 0. That is tin by itself, which is also a 0. By the way, this is oxygen with a -2, and that would be carbon with a +2 in this particular case. And if we look at this here, just look at the tin here is starting at +4 over here. It is ending at 0 in this case. It is becoming more negative, and that means the tin is actually being reduced in this case. The carbon here actually is starting at 0, ending at +2, becoming more positive. So the carbon here is being oxidized. What about the oxygen? Anything happening with it? No, it's the same on both sides in this particular case. That would mean in this particular case, our tin with a +4 charge is actually our oxidizing agent. And over here, our carbon, which is being oxidized, would be our reducing agent in this particular case. Any questions on that there? Now, we could do what we just did here, but there's also a couple other definitions of oxidation and reduction, and we don't use it a lot here in general chemistry, but you actually do use it a good bit of time over in organic chemistry if you're ever going to go that way, I suppose. So oxidation means, as we talked about, you can lose electrons. Another definition of oxidation is you can gain oxygen as you go from reactants to products. You could also lose hydrogen as you go from reactants to products. So if we actually just take a look at what's above there, we can also see our reduction definitions would be basically the opposite. We could gain electrons, we could lose oxygen as you go from reactants to products, and we can gain hydrogen as you go from reactants to products. So if we take a look up here at the tin has 2 oxygens here. It ends up with no oxygens, which means the tin has lost oxygen as it's gone from reactants to products and it's going through reduction. If we look at the carbon, has no oxygen there, but gained some oxygen there. And that is the definition of oxidation. So these other 2 definitions of oxidation and reduction honestly are used a lot more in organic chemistry, and that's because there's really not a lot of metals happening there. There's a lot of non-metals, so sometimes it's a lot easier to follow what's going on in terms of did this thing sort of gain hydrogen, lose hydrogen, gain oxygen, or lose oxygen. So in organic chemistry, those definitions of oxidation and reduction are probably used more than the loss and gain of electrons. Any questions on that? Yeah.
Gaining an oxygen, but oxygen with a -2 charge, why would gaining the oxygen be in the same category of losing it?
Yeah, so there are different things. So by the gaining of an oxygen, what it does is because it's negatively charged, it makes whatever gained it more positive, and that makes it more going through an oxidation in that case. Yeah. Other questions? All right, so now that we sort of have the idea there about oxidation reduction, let's talk about really the proper way, again, just to make sure everybody's on the same page, and how we assign oxidation numbers, which are sometimes referred to as oxidation states. And oxidation numbers, oxidation states are kind of the same thing. They are essentially the charge the atom would have if all the electrons were transferred. Now, sometimes people are confused about oxidation state and charges, and they can be different. And sometimes people, for example, when they start doing oxidation numbers or states, they have in their head the whole ionic compound type situation. Like, for example, chlorine. We think of chlorine as a -1 because it's group number 7 on the periodic table. And that is absolutely the case when chlorine is in an ionic compound. But when you put chlorine in a covalent compound where they're sharing electrons, there's no electrons being transferred. Something like chlorine could actually take on a positive sort of charge or a positive oxidation state. So keep that in mind. If it's not like an ion or if it's not an ionic compound, these elements may have some different oxidation states that you might think of when you think about it in an ionic compound. So the first rule is pretty much if you have any element that's by itself, uncombined, it will have an oxidation number of 0. If you have just say ion there, like I had earlier, iron 3 and iron 2, whatever really the charge of that ion is also its oxidation state. Now, oxygen is usually involved in a lot of places, and oxygen a lot of times is really the good place to start with when you're assigning oxidation numbers, and it usually is -2. There is a situation where oxygen is not -2, and that's actually when it's not really oxygen, it's actually peroxide, like in hydrogen peroxide. Peroxide is O22 minus, yeah, so that's peroxide. And in that case, it actually will be a -1 oxidation state. How do you know it's peroxide? Well, I would say the extra 2 kind of hangs out a little bit more in those formulas. So H2O2 and A2O2, so you'll kind of see that extra 2 hanging out there, and you kind of know it's sort of peroxide. Now, the oxidation number of hydrogen is +1 unless it comes after a metal. And remember, if it comes after a metal, it's the negative version of hydrogen, which is hydride, which has a -1 charge. Like, for example, if you had LiH, that would be -1 and +1 in terms of the oxidation numbers. Everybody in group 1 is +1. Everybody in group 2 is +2. Fluorine is -1. Now, when you add up all of the oxidation numbers, they do need to equal the charge on the molecule or ion that you have. Obviously, if you have a neutral molecule, then they all need to equal 0. If you're doing it for some type of like polyatomic ion or something like that that does have a charge, all the oxidation numbers do need to add up to the charge that's on there. So let's take a look at our friend here, bicarbonate. That's what we call that here in chemistry, I think. So when you have sort of a 3-pack of elements here, if you will, and you want to assign some oxidation numbers, usually the good course of action is kind of go right, go left, and save the one in the middle for the end. Yeah. So when we have bicarbonate, this entire thing has a -1 charge, and that is what all the oxidation numbers need to add up to. So we do have oxygen here. So again, as I mentioned, that's a really good place to start. We know oxygen is going to be -2. There are 3 oxygens there, which means oxygen is kind of contributing an overall -6 sort of charge. We go far left, that is hydrogen, which is +1. So we have +1 for the hydrogen, we have -6 for the oxygens. Remember, it all needs to add up to -1 because that is the charge. That means in this particular case, our carbon is going with a +4 oxidation state. Now, it's really important, a couple things when you give the oxidation numbers. Hydrogen in this case should be +1. Carbon in this case should be +4. and oxygen should be -2, not -6. So when you are stating the oxidation number or state, it is just like the one thing by itself, the one individual sort of charge is what you want to do it. Also, you do need to, in oxidation states and numbers, give the charge. Yeah, so even if it's plus, you should write +1. If it's minus, you should write minus, not just numbers, because you don't want me to interpret it wrong, I suppose, when I'm looking at it. Yeah, so you should always put the charges with the numbers, positive and negatives, both should be included. Any questions on that there? All right, so why don't you try some here for each of these, give the oxidation numbers for each of the elements that are there. Okay, so let's take a look. We'll start here with the lithium oxide. Got oxygen, good place to start. So that's a -2. And lithium is group 1, which means it should be a +1 in this case. So a +1 and a -2 would be our oxidation numbers on that one. If we look at the next one, fluorine is always going to be -1. And because there's 3 fluorines, that gives us like a -3. The overall charge here is neutral, which means our phosphorus here is actually rocking a +3 oxidation state. Again, different than what you would think of phosphorus in an ionic compound, which would be actually -3. The reason for that is this is covalently bonded, and between phosphorus and fluorine, which one's more electronegative? Fluorine is the most electronegative, right? So basically, these fluorine atoms are sucking the electrons out of the phosphorus because they're sharing, and it's making phosphorus more and more positive because the electrons are moving closer to the fluorine in this case. Now, if we look over here, oxygen is -2, and that gives us a -6 here for our oxygen overall. Going to go to the left there. That's going to be a +1. So we got a +1 and a -2. Overall here, nitric acid is neutral, which means the nitrogen here is actually going to be a +5 in this particular case. Any questions on that one? Again, same idea here. Nitrogen in an ionic compound will gain 3 electrons, but here it is bonded to oxygen, which is right next door on the periodic table, and it is sharing electrons, and oxygen is more electronegative, sucking the electrons out of the nitrogen there, making it more positive in this case. So this is what I was talking about earlier in a covalent bonding situation where they're sharing electrons. Because they may be attached to things that are more electronegative, things we normally think of as being negatively charged can actually take on a more positive charge because of how the electrons are being shared. Any questions on that there? I was going to say, I think at the end of that sentence, but felt wrong. All right, so -2 there on the oxygen. That's 7 of them. That's a 14 negative. Overall here, we do have a -2 charge, which is what everything should add up to. That means that each of my chromiums here needs to be +6 in this case, right? +6 times 2 is +12, +12 and -14 is a -2. That is a winner right there. That's a +6 for the chromium and a -2 for the oxidation state of oxygen. Any questions on any of those there? Yeah. So again, if you got something that's more molecular, covalently bonded, sharing of electrons, you will see some oxidation states that are different than, like we talked about, kind of the ionic charges that you think of. Any questions on how to assign it? Super important to be able to assign oxidation numbers in order to balance redox reactions to see what's going on when we talk about galvanic cells and stuff like that, and understanding what is being oxidized and what is being reduced. Any questions on how to figure any of that out there? All right, so to finish up here for today, we're going to talk about how to balance a little bit more complicated redox reactions in either acidic or basic conditions. And we're going to talk about acidic conditions first, and then we'll make it basic. So if we wanted to balance this redox reaction here, really the first thing we should do is sort of split it off into its half reactions. So to do that is fairly straightforward. We just want to pick the two things on opposite sides of the arrows that have the same elements in it. So I got iron on this side, and I got me an iron on that side there. And on the bottom here, I got a dichromate or chromate happening, and I got a chromium over here. Now, before you get too far into this, what you want to do is maybe figure out what is going on. So in this particular case, when we look at the iron, it is +2. We just did this guy a second ago. That's -2 for the oxygen, +6 for the chromium. The iron here is a +3, and the chromium is a +3. So if we roll out the number line to see what's going on, iron is starting at +2 here and ending at +3 in this case, which means it's becoming more positive, which means the iron here is going through oxidation. By default, that means the chromium is being reduced. I can figure that out by looking at the chromium is starting at +6 and ending at +3, which means it is becoming more negative in this case and is going through reduction. So this right here is our oxidation half reaction. This is our reduction half reaction. By the way, my reducing agent would be what thing here? Yeah, the iron is my reducing agent. The dichromate or the chromium is my oxidizing agent in this particular case. All right, so once you have it split off into its half reactions, the next thing you want to do is balance all the elements except for hydrogen and oxygen, and we balance it exactly like we balance an equation. So in this case, we have one iron on the left, one on the right, so it's good. But we do need a 2 here for our chromium, as we have 2 chromiums on the left and 2 on the right. Now that we've balanced all the other elements, it is time to balance oxygen. And the way we balance oxygen, maybe this will ring a bell, is we like to add water to balance the oxygens. And we add the appropriate number of waters to whichever side needs the oxygen. Now, when we do add water, we're not just adding oxygen, but we are adding hydrogen as well. So to the opposite side of where you add the water, you need to add 2 H pluses for every water that you put in there. So let's see how we do that on this one here. Top half reaction, there is no oxygen on either side, so that's good. Bottom half reaction, there are 7 oxygens on the left and none on the right, which means the right-hand side gets 7 waters. Now that I put 7 waters on the right, I have now also put 14 hydrogens over there. That means I need to go to the left-hand side and put 14 H pluses. So again, opposite side gets H plus, 2 of them for every water that you add. Any questions on that there? Now that we balance the hydrogen and we balance the oxygen, and by the way, if you started out with extra hydrogen to start with, you could just add H plus to the other side to balance it out right up front, and it'll work out as well. Now that we balance all the elements, the next thing we want to balance is actually the charge on each side of these half reactions. They do not need to equal 0, but they need to equal the exact same charge on each side. The way that we balance out the charge is we then add electrons. So the easiest way to do this is just to look at the overall charge on each side and see which one needs the electrons. That is an overall charge here of +2. That's an overall charge of +3. That means on the right-hand side, I need 1 electron that's going to supply a -1 charge. That gives me a +2 on the right to match my +2 on the left. Now, when I look at the bottom, I got 14 positives here. I got actually a -2 overall. No need to go element by element because the overall charge does that for you. Why do the math? That gives me a grand total over here of a +12 happening if I add up everything. 2 times 3 is +6, and water is 0, so I have a +6. The side that needs the negative charge is the left-hand side, and I actually need 6 electrons over there. That is going to give me 6 negatives. 6 negatives and 12 positives is a +6 and a +6. I am now balanced on each side. Correct number of charge on each side. I also know I did this correctly because the top half reaction is my oxidation half reaction, and I added my electrons to the correct side. That is the product side. Bottom one is my reduction half reaction. I added it to the correct side over there, and that's a good way to do it. Again, if you're at this point and you add it to the same side, the nicest way I could say that is you screwed up. Yeah, so you messed something up when you did that. I am actually ready at this point to add these back together. But before I could add these back together, as we talked about, you need the same number of electrons. And in this case, we do not have the same number of electrons. This guy's got 6. This one has 1. That means for the top equation, we need to multiply it by 6. And if we do that, let me just get rid of some of this here. So I can write it underneath, I think. All right, so if we do that, I'm just going to rewrite the top equation underneath. Multiplying by 6 gives me 6 of the iron 2 goes to 6 of the iron 3, gives me 6 electrons. Now I have the same number of electrons on each half reaction. Now I can add them together. Completely cancels the electrons, and if it doesn't completely cancel, again, you did something wrong. They should completely cancel out. Everybody on the left stays there. So 14 hydrogens plus Cr2O72 minus plus 6 iron 2s. Everybody on the right stays there. 2 chromiums plus 7 waters plus 6 iron 3s. If I did this correctly, this should be balanced in acidic conditions. How does this equation has to be balanced? It has to be balanced like a normal equation, which means you have the same number of elements on each side. That is 14 hydrogens there, 14 there, 2 chromiums, 2 chromiums, 7 oxygens, 7 oxygens, 6 irons, and 6 irons. So it is balanced like a regular equation. It also has to be balanced charge, has to be the same on both sides. Overall here, that is a +14 from the hydrogens. That's a -2 for the chromates. And that is a +12 for the iron. That is a lot of math. At 26 minus 2 is +24 for the left. On the right here, that is +6 for the chromiums. That is +18 for the irons and 0 for the water. Gosh, I hope that's 24. It is. And this would be balanced then in acidic conditions. By the way, how do I also know it's balanced in acidic conditions? What do I see there? CH plus, yeah, so that is how you know it's balanced in acidic conditions. Any questions on that? We'll save going to basic for next time, something to look forward to. All right.